pretty big transition into something different. And of course, not wildly different. We're still talking about sine, cosine, tangent. I guess I wanted to start with the concept of writing a proof, and I was thinking about those questions we did on the board work, where I asked you things like, does the tangent of a plus b equal the tangent of a plus the tangent of b? Remember that you have a very powerful tool in your calculator that can kind of easily prove or disprove, can easily disprove things or be a source of evidence, right? All I'd have to do is pick a value for a and b and see if it's true, right? Give me two numbers for a and b. They don't need to be special numbers at all. 2 and 3. 2 and 3. So does tan 5 equal tan 2 plus tan 3? I mean, you can check that in your calculator in 5 seconds. So if you're confused about something, your calculator can be a tool to help you get some clarity about it. But that's not a proof. That's just a piece of evidence. Let's take something that we've already talked about today. A plus b times a minus b equals a squared minus b squared. That's called the difference of squares. And generally we use it going this direction, where we look at something that is the difference of squares and we say, aha, I could factor that and make use of that. If I want you to prove this, well, again, we could start numerically and kind of think about some numbers like, well, if a equals 10 and b equals 1, does this work? Does it make sense? 11 times 9 equals 99. That's 100 minus 1. Well, that seems to work. We could try a bunch of numbers like that. But again, that's not a proof. That's just some particular evidence. When we build proofs, what I want you to do is take the equal part and move it down the page. And then your job is to connect these two. So to do things that get you from here to here. So we're not thinking of this as an equation. That's important. We're not doing the same thing to both sides. We're trying to go from where we're starting to where we're finishing. Or sometimes you'll find that looking at where you're finishing and working backwards can be a helpful way to get back to where you're starting. Now, this is not a complicated proof. What do we need to do to show that this is the same as this? Well, we just need to multiply it out, right? A times A is A squared. A times negative B is minus AB. B times A is BA. B times negative B is negative B squared. And then all we have to do is to recognize that minus AB plus BA is equal to 0, because the order of multiplication doesn't matter. And there we are. Boom, we're done. Right. These two terms cancel out. If we really wanted to be very particular about it, we could just point out that minus AB plus BA has to be equal to 0, and we're there. So very simple proof that A plus B times A minus B gives us A squared minus B squared. Well, let's think about what we already have in our toolbox in regards to trigonometry. We know a lot about sine and cosine. We know what they look like. We know that this one is even and this one is odd. You remember what that means? Those are symmetry terms. So sine of theta is odd. That means sine of negative theta equals, what's that? No, sine theta is odd.
So that means sine negative theta equals negative sine?
Right. The negative pops out and it escapes. Cosine theta is even. That means that the cosine of negative theta equals cosine theta. We know tan, secant, cosecant, and cotangent are all mixtures of sine and cosine. Can you write them all down from memory?
But we wouldn't call them symmetric, right?
Wouldn't call what symmetric?
The tan, secant, cosine. I mean, I don't know. The four that you just put down, I mean, because you said odd, even, and then you wrote four others. Are we labeling them as non-symmetric or?
No, I'm just saying, what do we know?
Okay, sweet. Okay, I got you.
We know that this is odd, we know this is even, we know that these are combinations of sine and cosine, so they can all be defined in terms of sine and cosine. And you're kind of getting on to my point, which is that from that knowledge, then if we want to know, hey, what is the symmetry of tangent? We can work it out in terms of sine and cosine, because we know tangent is sine over cosine. Then we can apply the symmetry of each one individually. So what happens with the negative here?
It comes out.
It comes out. And what happens with the negative in the cosine?
Looks like it goes away.
Goes away, it eats it up. So this ends up being negative tangent theta, which means this is the definition of an odd symmetry. So what we're going to do in this section is we're going to look at some ideas, and then we're going to try to kind of prove new identities or qualities or equivalents. So for instance, we talked about the Pythagorean theorem and how the Pythagorean theorem can be converted into a trig statement. But there's actually three versions of that Pythagorean theorem in trig. Prove 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so we're going to take this part, we're going to move it down here, cosecant squared theta, and then we're going to try to connect the dots. How do we show that this thing is the same as this thing? Well, I would start with the fact that we know that cotangent is a mixture of sine and cosine. So let's rewrite cotangent in terms of sine and cosine.
I'm sorry, can you say that again?
We know that cotangent is a mixture of sine and cosine. Because all of these, tan, secant, cosecant, cotangent, all just variations on sine and cosine.
Oh, yes. So cotangent is cosine over sine.
True. So we'll make a replacement. So 1 plus cosine squared over sine squared. Or if I was going more slowly, cosine theta over sine theta squared. When I multiply by itself, top multiply by the top, the bottom multiply by the bottom, it's going to be cosine squared over sine squared. Okay. I need more room. Feeling like I need more room here, so I'm going to move this down. Now what? Let's add these fractions together. How do we add fractions? Oh, this isn't a fraction, but I can make it a fraction, right?
Can you make that sine squared over sine squared?
Absolutely. And then have a common denominator. So multiply the top and the bottom by sine squared. Sine squared theta plus cosine squared theta over sine squared theta. We're almost there. Probably you want to have in your pocket one of the Pythagorean identities, which is the most basic one involving sine and cosine. Remember what it is? I'll give it to you. Sine squared plus cosine squared equals 1. So therefore the top is just 1. And we have 1 over sine squared theta. And is that the same as cosecant squared theta? What's cosecant?
That definition you wrote over here on with your circle, that's just a definition that we just have to know? Or that's
I'll give it
like,
to you. That's the Pythagorean theorem in Trig. That's the main.
oh, okay, thank you.
We looked at it before, but it was a couple weeks ago. So is 1 over sine squared the same as cosecant squared?
So, yeah.
Yeah, because cosecant is 1 over sine, so cosecant squared is 1 over sine squared. So that's a proof. That's a different Pythagorean identity, a different version of it. That 1 plus cotangent squared is cosecant squared. And that's a series of steps that gets us from one to the other. Okay, let's look at another one. I'm gonna put over here helpful hints that we kind of gather as we go through some Pythagorean identity is going to be useful. We need to know the even and odd symmetries. Add fractions was a key step there, right? We're kind of sitting there and like, what are we going to do? We've done the replacement for cotangent. We're like, but if we added the fractions together, get the common denominator, then things started to work out. All right, let's take a look at tan theta cosine theta equals sine theta. This one doesn't take quite as many steps. Again, taking this, we're moving it down. We want to prove that tan theta cosine theta is sine theta. Very basic. Replace tan, cotan, secant, cosecant with sine, cosine. So it should be one of your first moves is just simplifying everything in terms of sine and cosine. So what would you do here?
So that one, 10 is sine over cosine.
Place tan. Good. So my next line would say sine theta over cosine theta times cosine theta. Maybe make this a fraction. You need any more lines to get to sine theta? Multiply across because it's multiplication of fractions. And we get some cosine simplification. So we got sine theta over 1, which of course is sine theta. Done. Let's try another one. This is hard in the sense that the math feels different than what you're used to because you're used to solving a problem, give an answer. The point here is to start at one place and end up at another place. Okay? We're not solving an equation. We're proving something. I think this one you guys can do on your own. Just using that same basic point, which is let's replace any tan, cotan, cosecant, secant with sine and cosine. Wow. How about that? Wow. This thing is not there. Very zippy. A minute for that. I'm going to put up the next one.
I'm sorry, on that one on the left, I actually can't see the first value.
Scrunch it up. 1 plus sine x. So having to use your and that turns into something. Yeah. Okay. Anybody need help with that first one? Somebody want to walk me through it? It's your time to shine.
First thing you do is turn cosecant to 1 over sine theta times cosine theta over 1 times sine theta over cosine theta.
Yeah, nice. Make everything fractions, then you can see the simplification. And a bit more. Cool. All right, need more time on this next one? Do you think you got it? Got a little even odd symmetry part in there that you got to deal with.
Do you just have to replace the 1?
Are you talking about the 1 plus sine x times 1 plus sine minus x?
So we have to use the Pythagorean one that you used before, I assume, yes?
Yeah, but not that way, right?
Not right away, right? That's the last step I just had to use it last. I was lost, and I was like, oh, I could use that. Okay.
Pythagorean
Sweet.
Okay, I'm gonna put up another one. Amen. Fraction skills are really critical here. So one of the things that we're using is, we know we've got sine, cosine, tangent. This is sine over cosine. And then we've got 3 mirror functions, which are reciprocals of those 3.
Which is in the middle.
Cosecant, secant, cotangent.
And cotangent. What's cotangent?
You mean, what does it look like graphically, or you mean what is it made up of in terms of sine and cosine? So the way I remember things is that everybody gets a co. So there's 3 pairs, and each pair has a co in it.
Okay.
So if you write down on one side sine, cosine, tangent. Then next to them, you can make their partners. So cotangent obviously goes with tangent. COT. Then you've got cosecant and secant. Everybody gets a co. So the one that doesn't have, then both of them have co's. So I want every pair to have a co. So sine goes with cosecant, and cosine goes with secant. CSC is cosecant, and SEC is secant. So C and A. So the point of having this structure is that it helps you know that cosecant is 1 over sine, secant is 1 over cosine, and cotangent is the flip of this. What's tangent? Well, tangent is sine over cosine. So I would write them all down in their fraction form. Okay, let's take a look. So what's the first thing you probably do on this one? Deal with this odd situation. What's sine negative x?
Negative sine x.
Negative sine x. So that negative can pop out. So we got 1 plus sine x times 1 minus sine x equals cosine x. Bring my cosine squared down here. All right. Multiply it out. That is the difference of squares. 1 minus sine squared x. You can multiply it out if you want. You get that cancellation in the middle, but you're free to use your knowledge about the difference of squares to just jump right to it.
And then if you were to add it sine to the other side.
Okay. Okay, it's not an equation. But we can use, there's a couple ways we can do it. We can use sine squared plus cosine squared equals 1. So we could replace 1 with sine squared x plus cosine squared x. Right? Or I'm happy with just knowing that if I just manipulate the Pythagorean identity, right? If sine squared x plus cosine squared x equals 1, then cosine squared x equals 1 minus sine squared x. This is an identity. So 1 minus sine squared x is the same as cosine squared x. Or replace this sine squared x plus cosine squared x minus sine squared x. Okay, cosine squared x. A couple ways to finish that. All right, you had some time to think about this secant squared situation, or you need more time? A little more challenging here. And there's different ways you could go. There's not one set path. Anybody get there? Nobody got there. Or else you don't want to tell me.
Nope, I'm stuck.
Well, let's see. Even odd symmetry is not going to work. Add fractions. We don't have any fraction. Well, we could have fraction if we replaced sine and cosine. You know, what is secant in terms of sine and cosine? But also, why don't we just simplify this by distributing the division? I mean, secant squared divided by secant squared is 1, right? So if we just distribute the division, you're going to end up with 1 minus 1 over secant squared theta. Now, that doesn't look very good, but now might be a time to plug in our sine cosine. What is secant in terms of sine and cosine? 1 over cosine. So we're going to have 1 over cosine squared. Again, fraction skills coming into play here. What is 1 over cosine squared? We're going to simplify it.
Is that just cosine squared?
Yeah. And here we are. Basically the same place we ended up last time, just with. Now, if you'd made the replacement originally, you know, it just would have gotten messier, but you still could have handled it. You would have had 1 over cosine squared in 2 spots. And then you got to kind of work through. You know, I could have done division by 1 over cosine squared, which is multiplication by cosine squared, and then that'll clean all that up and leave you with 1 minus cosine squared. So there's a bunch of ways to get to that spot. Don't feel like you have to find the way. Okay, last one. Sine squared minus 1 over tan sine minus That's supposed to equal sine theta plus 1 over tan theta. Right, so remember this guy come down here, we're not doing the same thing to both sides. We're going to try to operate. Sorry, that first term here, this is tan theta. Bunch of ways to get there. What's tan? So what's cotangent? So tangent is sine of cosine.
Yeah, but isn't cotangent just tangent?
The flip. So what's cotangent?
Tangent.
No.
When you say cotangent is tangent, so what does that mean?
Well, if I say take 2/3 and flip it, okay, that's what I mean. What's tangent?
Sine of cosine.
Okay, so what's cotangent?
Tangent.
Flip of tangent.
Flip of tangent.
You might want to write it down. Just write tangent equals sine of cosine. Okay, now tell me, what's cotangent?
The flip of tangent.
Yeah, but I want to hear it in terms of sine and cosine.
Cosine over sine.
There you go. Okay. What's secant?
Cosine.
That's the flip of cosine. So you gotta see it's cosine of 1, which means secant is 1 cosine. Cosine.
Over sine.
Yeah, that's your 6 trig functions. This is the minus, not a times. Oh. Is this cosine squared or is this minus? Think about taking the 1 over here, sine squared minus 1, and this goes to the other side, that means negative cosine. Anybody crack this baby open? Give you a hint. Factorization would be a really neat way to get there. Without losing your mind. Here, replacing tangent with sine over cosine, you know, it'll still get you there, but it's going to make it harder in a way. Partly because of where you're going to end up. The desired goal has something to do with your strategy. Give me another minute. tell me a little bit about where you see factorization.
In the denominator, you can factor out the tan.
Common factor 10 in the denominator. Does that inspire anything? Write it down and look at it.
A bit closer, but you can't, I didn't know what to do after this part.
Any other factorization you see? Difference of squares, difference of squares. Keep a little puppy, little difference of squares.
Sine theta,
50
plus 1.
There you go, there you go. Sine theta minus 1, sine theta plus 1.
Oh,
Sine theta minus 1. Boy, you love those difference of squares. So if you got in deep on the sine cosine replacements here, you really probably went into a rabbit hole of pain and misery. It's not always the right thing to do. So we're adding to our toolbox in terms of thinking about what else is there for us.
I'm confused on how you got the denominator for the second fraction right there.
We factored out tan theta here, here. So bring it out. What's left? Sine theta, because tan theta, sine theta is tan phi. And then minus 1, because we factored that out, which is dividing by tan theta. What's left is 1.